The mathematics, we're still on calculus as our point of focus, and today we'll look at what we call affine subspaces, and then also look at the topic of quotient spaces. So if you have any question, please feel free to leave a comment in the comment section. I'll really be slow on this so that we clearly understand what we're trying to do here. But other than that, it's really an absolute pleasure to be doing this. And yeah, let's start. Before we proceed, let's remind ourselves what an equation of a plane is. And we previously derived the equation of a plane, and we said it is a linear functional, and that is the sum of a product of a constant ai, a real number, and coordinate point xi, which is equals to L, where ai is a real number and xi is a point on the coordinate, right, of the plane that we're interested. Let's call it n. And this derives from, let's say, we do have a three-dimensional Cartesian space, and we do have a vector from the origin to a point A, and let's say we do have a plane that we're interested in, right? On that plane, if we do have a point x, so that we have x1, x2, x3 as our coordinates, and again if we do have another point b that we have coordinate points that we know, x is an arbitrary point on that plane, any point on the plane, then it means that if the vector bx or bx or xb, if this vector is perpendicular to OA, since we know that the scalar product of two vectors, so if we have vector A and B, the scalar product is 0 if A is perpendicular to B, right? So from here we have an unknown x, which is an arbitrary point on the plane, and we have a known point b on the plane. So we can say, okay, the vector OA, right, and the vector bx, when you get the scalar product, that is 0. So let's denote OA with vector A, and sometimes I use an arrow just to indicate a vector. And then here we have vector bx as vector x minus vector b. Sometimes you can put an arrow on top, but sometimes let's assume that these are vectors. So this is 0, as we know, so that ax minus is equals to 0. So in other words, ax is equals to a dot b, and ax, just to continue here, if ax be equal to ab, and these are constants, this is a scalar product of known points or known vectors, then it means that this is the same as ai xi, where I is from 1 to 3 equals to L. And this here is the equation of a plane that we saw previously. And this is important. This is very crucial. It's going to inform what we're going to be looking at today, going forward. We saw what the equation of a plane looked like, and that is the summation for a three-dimensional space I equals to 1 to 3 of a I x I being equal to a constant L. And previously we saw that when L equals to 0, x equals to 0, this means that xi, these belong to a vector space V. And this was considered to be a null space of the linear functional that we saw here. However, we also saw that the points that we see here in the vector space, when given a parallel translation, would move back to this equation of a plane, because then we're just adding a vector to every point, a specific vector to every point on the points on the vector space. And so there is a translation of that plane from the vector plane to what we call affine spaces. So that translation was seen to be, or to be called, a parallel translation. So if we have a vector space n, and then we added the constant or whatever vector there, that now means that we are translating something x, that's to a new plane on a affine subspace that is going to be y, and that is member of n plus L. So we're going to be looking at this in this session today. If you have any question, feel free to reach out to us, and we'll clarify these foundational aspects of what we're trying to look at today. So let's talk a little bit about the affine spaces. Now, let's assume that we have a subspace N that belongs to a vector space V, and then we have an alpha that is any vector of V. Then it means that when this set N plus alpha, in other words, we've added a vector to the subspace N that is equal to any point psi plus alpha, and psi is any point in the subspace N, and this is called the set of points that have been now created or translated into, it's called the coset of N containing alpha. It's also called the affine subspace of V through alpha and parallel to N. Just a quick example is if we have the coordinate z, and then maybe this is x and this is y, and we have a plane that is right on the xz plane, and then we just add a vector alpha so that every point are translated by the same magnitude, it means that we're going to create another plane that is pretty much parallel to the previous plane or the subspace n, and this now is obviously n plus alpha. It's also very interesting. We can also say that the set n plus alpha is also called the translate of n through alpha. If n is given and fixed, we shall use the notation alpha bar as this new subspace n plus alpha. Let's look at some of the properties of affine subspaces. The first is with a fixed subspace n, if we assume that alpha gamma is any point on the new subspace n plus alpha, then the translate of n through that the vector created by the points from the previous location. In other words, if the point is here, so this vector to this point here, when you add it to the previous set of points in n, you come back to the same n plus alpha. And that's why we're saying that alpha bar equals to gamma bar if alpha is a point on the alpha bar. Now, with n fixed for any alpha and beta, either alpha bar equals to beta bar, and that alpha and beta, these are points, or alpha and beta are disjoint. So this new created cosets or this new created affine subspaces, they're either coincident or they're separate and disjoint. So these are some of the properties. We'll continue looking at other properties as we go along. Let's continue on the properties of affine subspaces. We said if one of them is if we let this H, the fractal H symbol, be the collection of all affine subspaces of V, and what it means that this fractal H is that's a set of all vector subspaces of V. Then the intersection of any subfamily of H or fractal H is either empty or itself an affine subspace, which is straightforward. So if you have like all these translational points of a specific subspace, that it covers the entire vector space of V, then it's just obvious that H is that's a set of all vector subspaces of V, right? So that is obvious. Another one is if A and B are elements of H, fractal H, then A plus B is also a member of H, right? That is, the sum of any two affine subspaces is itself an affine subspaces. Affine subspace. Then, this is obvious. If we have a subspace, if you have 2 points and then you add those 2 points, you just get another point that's within. That's also a member of the subspace we are looking at. Now, if A is an element of H, fractal H, and T is this linear mapping, we saw what a homomorphism of VW is, which is just a linear mapping from the V vector space to W vector space. So if we have A being an element of H, and T is a function. It's one of the functions in the homomorphism from the V vector space to W vector space. Then TA is an affine subspace, the transformation, that linear mapping of any of a point A is an affine subspace of W. So we've moved A to the W space. In particular, if, for example, T, a real number, is multiplied by A, that still means that that product is still a member of the fractal H. Another thing is, if B is an affine subspace of W, if B belongs to W, then taking one of the functions within the homomorphism VW, the inverse of that, assuming that T is surjective, it means that either that inverse transform is either empty or an affine subspace of V. Right? That's one thing we need to know. And then one other thing we would love to know is, for a fixed alpha that's a member of the vector space V, the translation of V through alpha is a mapping S alpha, which is V unto V, because alpha belongs to V, and that vector is within space V, and you're moving the entire space V through alpha, which is a vector within V. That means you're translating from V to V, or you're transforming or mapping V to V, and that is defined as S alpha, and we see xi here being equal to any point psi that is in V added to alpha for all xi that are elements of V. So that's an interesting one as well. This is important to ourselves, is that an affine transformation of a vector V to a vector space W is a linear mapping from V to W followed by translation in W. And we could make this a little bit clearer. Let's say we have a transform of the sorts, right, as beta, right? And T here is a homomorphism that covers that linear mapping from V to W. Then there's this beta here that is the translation in W. And beta here is just simply, an element of W. So one thing, we could also maybe look at is, if we have this transform, T chi plus alpha, this is equals to T, because we're looking at a linear mapping. This translation is also an affine, transformation. Yeah, because obviously this here is a translation into the W space, where alpha is an element, of V. I mean, let's not confuse ourselves here. But I think we get the gist of it. Affine transformation. We know what we know affine subspaces. We know what a parallel translation. We know what a translate is. We know what cosets of n containing alpha. We know all that. So the next topic we want to look at is what we call the quotient space. For example, suppose that we have a subspace n and we fix it, and n belongs to the vector space V. Then let's consider the set W of all translates, cosets of n. So what happens is that W is itself now a vector space, right? It's a vector space. Because now it's this global thing that consists of all these translates, these cosets of n. For example, if n is a line through the origin in the three-dimensional Cartesian space, then W consists of all lines in the same space parallel to n. So you can imagine if you have this one line through the origin, and so you have these lines in all directions created by the shifts that has been brought about by adding a vector. Then this set of parallel lines will automatically turn out to be a vector space. The sum of all lines will automatically turn out to be a line W. So assume that L is a member of this new space W and T is not equal to 0, then the set product TL is a line still in W. The translates of L do fiber R. In other words, it's and you know what a fiber is? A fiber of a global set is just a disjoint, one disjoint set within the global. So if let's say you have 10 disjoint sets, 10 dissimilar sets, basic dissimilar sets in a global set A, then that individual set is a fiber. So the translates of L create these disjoint sets that would end up making the vector space R23. And the set of fibers is obviously a natural vector space, the entire set of these lines. Okay. So we're going to prove a theorem here, maybe just state it. That is that let V be a vector space, right? And there is a mapping from V to W. So V is a vector space and W is a set having two vector-like operations. And we know what vector-like operations are: addition, multiplication by a constant, which we designate in the usual way. Suppose there exists a surjective mapping T that takes something from a vector space V to a set W, which preserves the operations T S alpha plus T beta being equal to S T alpha plus T beta. So then we are told that W should be a vector space. The important part here is we're showing that we are moving from a vector space to another vector space, but that vector space in which we're moving into has a 0 point. You know. So one way we could do that is by saying, okay, if we do have a scenario like this, right? So where we have this constant coming out, then we could take, for example, TB to be 0, and so we could also have being equal to ST alpha, right? And the moment this S is set to 0, because we're saying that S here is the real number, then we see that T0 equals to 0. So the T0 here, the 0 in the V space is translated to a 0 in the W space, and essentially what is happening here is that because W is a vector space, but also has a null it has a 0 or a null space, then W is a vector space. So that's an easy proof for us. So the important one, just a couple of theorems to keep us keep the concepts in perspective. One of them is that the set of cosets of a fixed subspace N of a vector space V themselves form a vector space called the quotient space. Under the above natural operations, and the projection pi, we talked about coordinate projection. Projection pi is a surjective linear map from V to Vn, and Vn is that quotient space. So what essentially we are seeing here is that there is, a set of all these translations from the N subspace, yeah, and that forms a vector space within N, and that is called the quotient space, right? And then there's that projection, the coordinate projection pi that we have here, which is a surjective linear map from V to Vn. Then the next theorem is that if we have this T, that's a mapping, linear mapping in the homomorphism VW, and if the null space of T includes the subspace M, which is a subset of V, then T has a unique factorization through Vm. This is the quotient space Vm. That is that there exists a unique transformation S in the homomorphism from the quotient space created by all the translation from the subspace M that forms the space in V into W. And we can extract that through this projection where we have S projection, or S constituted with pi is equals to T, right? And the last one is that if a subspace N of a vector subspace V is carried into itself by a transformation T in the homomorphism V, V to V, then there is a unique transformation S in the homomorphism Vn such that S pi equals to the projection is the same as pi constituted with T. So this may be abstract, but we will keep building on these principles going forward. A few things into perspective. We saw that if we had a subspace n, and this subspace belongs to a vector space V, and then we added any vector in the vector space V, still we get this new subspace that consists of a set of points such that we have chi here that now have been transformed to chi plus alpha, psi plus alpha, such that xi are elements of the vector space. Not the vectors, but the subspace N. Now we call these cosets, this new set is cosets of N containing alpha. We also may have called them affine subspaces. Of the vector space V through alpha and parallel to N. We may also have given it a name as the translate of N through alpha. And when one way of looking at it is if you have, for example, a sphere or a cube that is, centered around the origin, and then you added any given vector, that cube will be transformed in the direction of the vector that you add in, but still maintaining the cube form, and also if it's a sphere, it maintains the same shape. So that's how you could visualize it. So we now know what affine subspaces are, right? We know what affine subspaces is. Then the next thing is what we call the quotient spaces, right? Yeah. For example, if you do have these subspaces that are created when you have the transform, when you have your transform by adding the vector, so you're creating a new subspace within the original space, and let's say we have N here as our subspace, right? And so if you have these multiple transformations created by adding these many vectors, you're going to create a set of points within the bigger vector space that are in itself also a vector space. So the space created by the addition of these multiple vectors is called a quotient space. And so, for example, if N is a subspace that begins the journey, then the quotient space within the vector space V is going to be V, the quotient space Vn. So this is the bigger gist of what we tried to cover today. We might have gone through some couple of theorems, but it's important for us to put these things into perspective by saying that yes, you can create a subspace. You can create a subspace by these multiple additions um, of the multiple vectors that are also obviously members or elements of the bigger vector space V. So the theorem for which we looked at that is that the set of cosets of a fixed subspace N on a vector space V themselves form a vector space called the quotient space V/N. Okay, so that covers it. Thank you so much for your attention. We will keep proceeding. We're still, trying to clean up what this vector space is all about, but in our subsequent lessons, we'll keep progressing into other things. Well, thank you so much. Until next time, keep it locked. Subscribe to our channel if you can. Leave a comment or a question. That way we'll be in touch. Bye bye.